Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we are going to hopefully see the results of all the efforts we have been putting into writing our light-culling system. We are going to try and visualize the number of lights per tile and finally use the results to light our scene. We'll also fix the bugs that we find while we are trying to get things working. The first thing that we can visualize is the number of lights per tile. This can be done in the same way as for the grid frustums, using the post-processing step. We need to update the post-process root signature so that we can pass the light grid buffer to its shader. This buffer contains the number of lights per tile and is used as a shader resource in the pixel shader. Then we simply need to set this root parameter before drawing the post-process full-screen triangle. However, we also need a function that returns the GPU virtual address of the light grid, so let's add it now. This is similar to how we return the GPU address of grid frustums buffer. While we are here, let's also add one for the light index list, since we are going to need it in our lighting code as well. This is all we need in order to pass this buffer to the pixel shader. Now we can modify the post-process shader to read from this buffer. Remember that each element in the light grid consists of two integers, the second of which is the number of lights per tile. The most common way of visualizing this is by using a heat map, and the easiest way to do so is to pay a visit to another engine's source code and get it from there. My go-to engine is called Wicked Engine, which is developed by Janos Turansky. Apologies if I didn't say that correctly. It's an open source C++ engine with a ton of features and yet very accessible if you want to look up how something is implemented. The features are showcased here on their YouTube channel, and there's a Discord server as well. What's also great is that there is a blog where he explains and shares his thoughts on how certain features are implemented. So I'd like to recommend this engine as a good resource to study for engine programmers. Today we are going to steal a bit of code from this engine, which is by the way MIT licensed, so we are not going to get into trouble as long as we give the well-deserved credits to the author. The code that I'm looking for is a little function for calculating heatmap colors, which is included in the light-culling shader. Here we can also see that the light-culling in Wicked Engine is inspired by the same source article as the one we used and has the same general flow. However, there are some optimizations going on here to speed things up. We'll do an optimization pass after this episode, and although our approach will differ quite a bit, I'll come back to this code and give a brief high-level explanation of how it works. But for now, we can just grab this function and repurpose it for our engine. So first we calculate the flattened tile index in the grid and get the number of lights. And then I'll copy this part of the heatmap function. I'll set max heat variable a bit lower and then use the number of lights to calculate what's basically a fractional index into this array. Then we can find the array element directly before and after this index using the floor and ceil functions. We can use the difference between the fractional index and its floor to linearly interpolate between the two colors. At the end, we blend this heat map color with the rendered image. We can call this function with the light grid buffer like this. Of course, before I forget, we give credits and add a link to where this came from. Now we can try and run the application. I'll turn off random lights, so we only have a couple of lights, which we put manually in the scene. As always, I need to fix my typos in the shader. And I was hoping that we would see something around here in the scene, but we don't. So let's investigate. First, I'll check if the light count value is correctly passed to the post process. I can set this to 10 and we can see that it colored the whole screen since all tiles now have 10 lights. So that checks out. Let me see if we are setting the dispatch parameters correctly. These look alright as well. Let's use random lights in order to add a lot of lights to the scene. Here we can see that there's something going on, but it doesn't look right. So I'm going through the shader code to see if I can spot anything out of order. Okay, here is the error. Here each thread should pick a light for intersection testing, not just the first thread. So we should use the group index here. And the same goes for this for loop. This looks better already, but we need to make sure by looking closer, so let's turn off random lights again and check our manually placed lights. I'll also darken the rendered image so that the heat map is easier to see. Well, that looks okay. Here we can see the tiles that are affected by 2 point lights and 1 spotlight. There is also another point light down here, but we can't see it because it doesn't intersect with any geometry. So this looks promising. Now we can use random lights again. However, I'm going to add another parameter here in order to scale the volume that contains the lights, so they are spread more evenly in the scene. This is what the heat map looks like with about 18,000 lights. And this is with 64,000 lights, where we also see a noticeable drop in frame rate. The frame rate remains about the same even if we turn off this sleep timer. This means that we are waiting for the GPU, which totally makes sense. Now that the light-culling shader seems to be working, we can use the resulting buffers and our light data in the pixel shader for proper lighting. I believe at this point we all know the steps by heart. So first add root parameters for the various light buffers from which we are going to read in the pixel shader. These are callable light buffer, which contains light properties such as color and intensity, and light grid and light index list buffers. The root signature is created per material in d3d12 content.cpp. So we need to add these root parameters here. I'll first put all of these together so it's easier to see what register numbers we are using. Then we add the root parameters for the 3 buffers, which are all attached as shader resource views. Next, we are going to set these root parameters in the gpass module. Of course, we have to include the light-culling header as well. We need to provide the light-culling ID for some of these functions, so let me put that in a local variable. Okay, that's all we need to do in the C++ side. Now we can add the buffers and read from them in our pixel shader code. We need to use the same function to calculate the tile index, depending on pixel position and the view width. I'm also going to factor out the lighting code into a function so we can reuse it. Here I'll start using a fairly common notation for various inputs and variables. For example, n is the surface normal for this pixel, L is the vector from the pixel towards the light, and V is the vector from the pixel towards the camera. Then we can write our Wang lighting using this notation. Please watch this video where I explain about Wang diffuse and specular lighting. Now we add 2 new functions for calculating the lighting with point lights and spotlights. For point lights, we subtract the pixel position in world space from the light position to get the light vector. Note that this vector is not normalized and has a length equal to the distance from the pixel to the light source. This dot product is the square of this distance. For debugging purposes, I'll write a lighting function without attenuation so that we can clearly see the border on which the light ends. This helps us to make sure that a light is not caught from tiles where the intensity is very low. We light the pixel if it's within the light's range. Here we calculate the reciprocal of square root of the light's distance to the pixel, which we use for normalizing the light vector. Finally, we can use the lighting calculation function to determine the color of this pixel and return the color. We'll write the code for attenuated lighting in the next episode. The code for spotlights is very similar. Here we only light the pixel if the light vector is within the cone of penumbra. I'm also multiplying the light color with some random small number in order to keep the light color from maxing out to white when we have a lot of overlapping lights. Now we are ready to use the results of the light-culling shader. First, we add back the lighting calculation for directional lights, since we deleted the code earlier. I'll also get rid of the ambient light, so we can see other lights easier. In order to get the light indices, we calculate the tile index for this pixel and use it to get the start offset within the light index list, as well as the number of lights from the light grid. Then we use each index in the index list of this tile to get the light data which we can use for lighting. We call the lighting function that corresponds to each type of light. I forgot to define the tile size for our shader, so let me add it here. I also have to set this macro definition to 1, otherwise we won't get any lighting. The view vector should be a 3D vector, obviously. And here, somehow I forgot to do multiplication. This may be a bit too dark, so I'm going to turn it up a notch. And now we can see the lights. Well, at least 2 of them, but one is missing, which is concerning. Let me lift the lights a little bit so they are just above the ground. The spotlight looks okay, but one of the point lights is looking weird. And upon closer inspection, the spotlights has the same problem as well. So there's something fishy going on here. Checking the shader code to see if everything is alright, but I can't see anything wrong with it. Let's use random lights and see how that looks. Well, that's rather nightmare inducing. Lowering the number of lights, we can see that not all lights get rendered, and the ones that do are looking weird, and not in a good way. Let's have a look at the buffers in the light-culling shader. Aha, here is the copy-paste error. When I duplicated this line, I didn't change the buffer type. Obviously, the light index list is an array of single integers. Now it looks the way it should be. I can turn off the light count heat map so we can see the lighting. And here we have it with 18,000 lights in the scene volume. Cool, huh? We do get a bit of artifacts for spotlights, but that's not because of a bug. It's because we are using a cone as a bounding volume, which isn't a good fit for spotlights with a wider cone angle. If we look at a single spotlight here, which I just updated to have a wider cone, we can see that it's missing the corners when we look at it from a certain angle. We are going to fix this as well when we optimize the culling shader in the next episode. I hope you enjoyed watching this video. As always, thank you for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.